we have a model of the universe that works almost unreasonably well. It describes how everything began, how it grew, how matter spread itself into galaxies and clusters, and the vast cosmic web we see today. And for decades, every time we built a better instrument and went looking for a place where this model might break, it held. It predicted patterns in the oldest light in existence before we could measure them. And when we finally did, they were there, exactly as promised. It is one of the great achievements of our species. But right now, there are three things it cannot explain, and that is what tonight is about. The first is a number that refuses to agree with itself. We can measure how fast the universe is expanding in two completely different ways, using two completely different sets of evidence. And the two answers do not match. Not slightly, not within the margin of error. They have been checked and rechecked, and the gap has only grown more solid. The second is a patch of sky that is colder than it should be. It was found in 2004, and for more than 20 years people have been trying to account for it. The most promising explanation was found a decade later, and when the numbers were run, it fell short. And the third is the possibility that dark energy, the force pushing the universe apart, is not the fixed constant we assumed. The largest survey of its kind released results in 2025, suggesting it may be changing over time. If that holds, a piece of the model has to be rewritten. Now, any one of these alone is just an open problem. Science is full of those, and most of them get solved unremarkably. But here is what makes tonight's story different. There is a theory, one of the most successful in modern physics, that has been quietly making an uncomfortable prediction for over 40 years. It says that if our understanding of the first instant of the universe is right, then ours cannot be the only one. Not as a fun speculation, as a mathematical consequence that is genuinely difficult to escape. So tonight, we are going to look at all three cracks properly. Then we are going to look at why the mathematics keeps insisting on other universes. And then we are going to ask the obvious question. If there were something beyond the edge of ours, what would we actually expect to see, and have we seen it? But I want to be very clear about something before we start, because it matters more on this topic than almost any other. There is a lot of noise around this subject. You will find videos and articles claiming a telescope has detected a neighboring universe, that we have found the wall at the edge of reality, that it is confirmed. None of that is true. There has been no such detection, and I am not going to tell you there has been. What we do have is genuinely interesting, and I think more interesting than the fiction. We have real anomalies, measured by real instruments, that our best model cannot currently account for, and we have serious theoretical work about what a boundary would look like if one existed. That is a case worth examining. It is not a proof, and I will keep telling you which is which the whole way through. Before we begin, one small thing. Many of you come back for these journeys but have not subscribed yet. If you would like to keep exploring the honest edges of what we know twice a week, just tap subscribe and turn on the bell so the next one finds you. So settle in and let the day fall away, because we are going to start with the thing our model got right, so that you understand exactly how much it means when it goes wrong. So before we break anything, I want you to understand what we are dealing with. Because it is easy to hear that a scientific model has problems and assume the model is shaky, this one is not shaky. It is one of the most successful things we have ever built. It is called the Standard Cosmological Model, and what it attempts is absurdly ambitious. It tries to describe the entire history of the universe from a fraction of a second after the beginning, through the formation of the first atoms, the first stars, the galaxies, all the way to the arrangement of matter across the sky tonight. One framework, the whole story, and the picture it gives is strange. According to this model, everything you have ever seen, every star, every planet, every atom in your body, adds up to only about 5% of what the universe contains. Around 27% is dark matter, something we have never directly detected but whose gravity we can measure. And roughly 68% is dark energy, which we understand even less. So the ordinary matter that makes up the visible universe is a thin garnish on top of something almost entirely unknown. That should sound like a model in trouble, but here is why nobody dismisses it. It makes predictions, and those predictions keep coming true. Let me give you the best example, because it is genuinely one of the finest moments in the history of science. Everywhere you look in the sky, in every direction, there is a faint glow of microwave light. It is the oldest light in existence, released about 380,000 years after the beginning, when the universe finally cooled enough to become transparent. We call it the cosmic microwave background, and it is the closest thing we have to a photograph of the infant universe. Now, that light is almost perfectly smooth, but not quite. There are tiny variations in its temperature from place to place. And when I say tiny, I mean about 1 part in 100,000. Fluctuations so small they are barely there at all. And the model predicted the exact pattern of those fluctuations. Not vaguely, not qualitatively. It predicted a specific structure, a particular set of scales at which the variations should be strongest and weakest, following from the physics of sound waves rippling through the hot plasma of the early universe. That prediction was made before we had instruments precise enough to check it. Then we built them. First, a satellite in the early 1990s detected the variations existed at all. Then a better one mapped them. Then a third measured them with extraordinary precision, and each time, the pattern that came back matched what the model said it should be. The peaks fell where they were supposed to fall. The relative heights were right. Think about what that means. Someone worked out, from theory, what the faint temperature ripples in light released 13 billion years ago should look like. Then we went and measured that light, and it matched. And it was not a one-time success. The same model predicted how matter should be distributed across the universe today, not scattered randomly, but pulled by gravity into a specific structure, with galaxies gathered along enormous filaments and vast empty voids between them. A cosmic web. When we mapped millions of galaxies to check, that is exactly what we found. The predicted architecture of the universe was there. So this is why the model is taken seriously despite being built mostly out of things we cannot see. It earned its place. Over and over, it told us what we would find before we looked, and it was right. Which brings me to why the rest of this episode matters. When a weak theory fails, nobody is surprised. But when a theory this successful starts failing in specific places, that is different. It usually means we are standing at the edge of something new. Every previous time physics has broken like this, on the other side of the break, there was a deeper understanding waiting, and this model is breaking, not everywhere, in 3 particular places. And the first one is the simplest and most stubborn of all. It is a single number, one of the most fundamental in cosmology, that gives 2 different answers depending on how you measure it. And after decades of work, nobody can make them agree. That is where we go next. So here is the first crack, and it is beautifully simple to state. There is a number that tells us how fast the universe is expanding. We can measure it 2 different ways, and the 2 ways give different answers. The number is called the Hubble constant, and it is one of the most fundamental quantities in all of cosmology. Everything traces back to it. How old the universe is, how big the observable universe is, how everything in it has evolved. Get this number wrong, and a great deal else shifts with it. Now, there are 2 completely independent ways to measure it, and I want to walk you through both, because the fact that they are independent is the entire heart of the problem. The first route starts at the beginning of time. You take that oldest light, the cosmic microwave background, and you measure its faint temperature ripples with extraordinary precision. Those ripples encode the physics of the early universe, the density of matter, how gravity was pulling everything around, how sound waves moved through the hot plasma. And once you have all of that, you can run the standard model forward. You start with the universe as it was, apply the physics, and calculate how fast it should be expanding today. That method gives an answer of about 67.4 kilometers per second per megaparsec, and it comes with a very small uncertainty because the measurements behind it are exquisite. The second route ignores the early universe entirely. Instead of calculating forward from the beginning, you go outside and measure the expansion happening right now directly. To do that, you need to know how far away distant galaxies are, which is one of the hardest problems in astronomy. And the solution is a chain of steps that astronomers call the distance ladder. It starts with a particular kind of star called a Cepheid variable, which pulses in brightness on a regular cycle. And there is a wonderful relationship here, discovered over a century ago. The slower a Cepheid pulses, the brighter it truly is. So if you time the pulse, you know its real brightness. Compare that to how bright it looks from Earth, and you can work out exactly how far away it is. Cepheids get you to relatively nearby galaxies. Then you use those galaxies to calibrate something far brighter, a specific type of exploding star that always detonates with nearly the same intrinsic brightness. Those explosions are visible across enormous distances, so they carry you much further out into the universe. Measure their distances, measure how fast those galaxies are receding, and you get the expansion rate directly. That method gives an answer of about 73 kilometers per second per megaparsec. So there it is, 67.4 from one method, 73 from the other, a gap of roughly 9%. And I know that does not sound dramatic. 9% in ordinary life is nothing, but in this context it is enormous, and here's why. It is not simply that the two numbers differ. It is that both come with uncertainties, and those uncertainties do not overlap. Each team has said, in effect, here is our answer, and here is the range we are confident it falls within, and the two ranges do not touch. There is a gap between them where neither measurement will go. That means one of three things must be true. Either the first measurement has an error nobody has found, or the second measurement has an error nobody has found, or both measurements are correct and the model connecting them is missing something. And this is not a new argument that flared up last year. This has been building for well over a decade, and it has gone the opposite way from how these things usually go. Normally, as instruments improve, discrepancies shrink and quietly disappear. Better data smooths out the problem. This one has sharpened. Every improvement in precision has made the gap more definite, not less. Both sides have gotten more confident in their own numbers, which means the disagreement between them has gotten harder to wave away. So naturally, the obvious response is to suspect a mistake. Someone must have miscounted something. There must be a subtle flaw in one of those methods, hiding in a step nobody has scrutinized closely enough. That is exactly what people thought. And there was a leading suspect, a specific weak point in the distance ladder that could plausibly have thrown everything off. So we built a telescope capable of checking it properly, and we went and looked. That is where we go next. So there was a suspect, and it was a good one. The weak point everyone focused on was in the distance ladder, specifically in how we measure those pulsing Cepheid stars. And the problem has a name: crowding. Here's the issue. When you look at a Cepheid in a galaxy tens of millions of light years away, you are not looking at an isolated star sitting alone in the dark. You are looking at a star embedded in a crowded neighborhood, surrounded by other stars. And if your telescope cannot cleanly separate them, the light from those neighbors blends in with the light from your Cepheid, which means you would measure that star as brighter than it actually is. And if you think a star is brighter than it really is, you conclude it must be closer than it really is. get your distances slightly wrong, and you get your expansion rate wrong. Now, the Hubble Space Telescope did this work brilliantly, but it had a limit. It sees invisible light, and its resolution could only separate stars so well. In the most distant galaxies in the sample, some blending was unavoidable, and astronomers corrected for it as carefully as they could. But a correction is an estimate, and if that estimate was systematically off, even slightly, it could have quietly bent the entire distance ladder. This was the leading explanation for years. It was reasonable, it was specific, and best of all, it was testable. All you needed was a telescope that could resolve those crowded fields properly and check the same stars again. That telescope is Webb. It sees in infrared, where crowding is less severe and its resolution is far sharper. So Webb could look at the exact same Cepheids in the exact same galaxies and measure them cleanly. So that is what the team did. They went back to the same stars Hubble had measured. Not a different sample, not a different method. The same individual stars, re-observed with a better instrument. And the results came back. The Webb measurements agreed with the Hubble measurements. The distances held. The crowding correction had been done properly all along. And when the team ran the numbers on whether crowding could account for the Hubble tension, that explanation was ruled out at a confidence level of 8.2 sigma. I should explain what that means, because sigma is one of those terms that gets thrown around without weight. 5 sigma is the threshold physicists treat as a discovery. It corresponds to odds of roughly 1 in 3.5 million that a result is a random fluke. 8 sigma is far beyond that. It is not close. It is a door being firmly shut. So the crowding explanation is dead. The local measurement of 73 stands. And take a moment to appreciate what actually happened there, because it is a lovely piece of science. A team had a result that was making everybody uncomfortable, including themselves. There was a plausible explanation that would have made the problem go away and let everyone relax. So they went and tested it properly with the best instrument ever built on their own work. They tried to prove themselves wrong, and they could not. The tension itself now sits beyond 5 sigma. By the standards physics uses for everything else, that means it is real. This is not a rounding error or an artifact. 2 rigorous measurements of the same universe genuinely disagree. So Webb did not resolve the crisis. Webb removed the most comfortable way out of it. And that changes the shape of the problem entirely. Because if neither measurement is wrong, then the fault has to lie in what connects them. And what connects them is the model itself. The step where you take the early universe and run it forward to the present day. Something in that journey, across 13.8 billion years, is not what we think it is. Nobody knows what. There are many proposals. Perhaps dark energy behaved differently in the early universe. Perhaps there is a form of matter or radiation we have not accounted for. Perhaps something else. None of them has won. So that is crack number 1, a number that refuses to agree with itself, with the easiest escape route now closed. But as I said at the start, one anomaly on its own is just an open problem. Physics has plenty. What makes tonight's story different is that this is not the only place the model is struggling. There is a second problem, in a completely different kind of data, discovered by different people using an entirely different technique, and it has been sitting unexplained for over 20 years. That is where we go next. So let us go back to that oldest light, the cosmic microwave background, because the second crack is hiding in it. Remember what this light is. It was released about 380,000 years after the beginning, and it has been traveling ever since. It comes at us from every direction in the sky, and its temperature today is about 2.7 degrees above absolute zero. Cold, faint, and almost perfectly even. But almost is the important word. There are tiny variations in that temperature from place to place, about 1 part in 100,000. And as we discussed, The standard model predicted the pattern of those variations beautifully. Here is the key thing to understand about that pattern. The model does not predict where any individual warm or cold patch will be. Those come from random quantum fluctuations in the infant universe, stretched to enormous size. What the model predicts is their statistics. How large the patches should typically be, and how deep. It tells you what the distribution should look like, the way you might predict the distribution of heights in a large crowd without knowing any one person's height. And the measured sky matches those statistics remarkably well, almost everywhere except in one place. In 2004, working through data from a satellite mapping the microwave sky, researchers found a region that did not belong. In the southern sky, in the direction of the constellation Eridanus, there was a patch that was too cold. It is about 70 microkelvin below the average. Now, that sounds absurdly small, and in absolute terms it is. But remember the scale we are working on. The normal fluctuations are already tiny. Against that backdrop, a deviation this size is dramatic. It is far outside the range of ordinary variation. And the second thing about it is the size. This region spans roughly 5 degrees of sky. To picture that, hold up your hand at arm's length. The full moon is about half a degree across, roughly the width of your little fingernail. This cold region is about 10 times wider than that. It is a genuinely large patch of the sky. Put those two facts together and you have the problem. A cold spot that deep, spread across an area that large, is not something the standard model comfortably produces. You can get small deep patches, you can get large shallow ones. But a region both this cold and this wide sits in the tail of what the statistics allow. They called it the CMB cold spot, and more than 20 years later, it is still there. Now, I want to be careful here, because the first response is usually to say, so what? In any random pattern, some region will be the most extreme one. If you flip a coin 10,000 times, you will find an unusual streak somewhere. Does that mean the coin is rigged? That is a completely fair objection, and it is exactly the argument some researchers make. If you go hunting through the whole sky for the most unusual feature you can find, you are guaranteed to find something, and the odds of finding an outlier somewhere are much better than the odds of finding one in a place you specified in advance. So the cold spot alone does not overturn anything, and nobody serious claims it does, but it was not dismissed, and here is why. When people calculated how likely a feature like this is under the standard model, the answer kept coming out uncomfortably small. Not impossible, but rare enough to be worth a proper explanation. And crucially, unlike a random coin streak, this is a physical region of sky. It has a location, which means you can go and look at what is actually there. If a large cold patch in the ancient light is caused by something real, then something should be sitting between us and that patch, doing something to the light on its way here. That is a testable idea. You do not have to argue about statistics. You can point a telescope in that direction and find out what is there. So that is exactly what astronomers did. And in 2015, they found something. Something enormous in exactly the right direction that looked like it could be the answer. For a while, it seemed the mystery was over. The explanation was found, the anomaly was accounted for, and everyone could move on. Then somebody ran the numbers properly, and that is where we go next. So astronomers pointed their telescopes toward Eridanus and mapped what was actually there. And in 2015, they found something enormous. It is called the Eridanus supervoid, a vast region of space where galaxies are unusually scarce, roughly 1 billion light-years across. One of the largest underdense regions ever identified, and it sits in the right part of the sky. And there is a real, well-understood physical reason why a void like that could cool the light passing through it. It has a rather grand name, the integrated Sachs-Wolf effect, But the idea underneath is simple. Imagine a photon from the early universe traveling toward us, and on its way, it enters an enormous region with very little matter in it. As it falls into that region, it picks up a little energy, the way anything gains speed falling into a valley. Then it has to climb out the other side, which costs energy. In a static universe, those would cancel exactly. In, out, no net change. But our universe is expanding, and the expansion is accelerating. So while that photon is crossing the void itself is stretching. The far wall it has to climb has grown shallower by the time it gets there, so it does not have to pay back everything it gained. It comes out having lost a small amount of energy overall. And light that has lost energy is light that arrives slightly colder. So the story assembled itself neatly. A gigantic void sits in that direction. Light from the early universe crosses it, loses energy, and arrives here looking cold. Mystery solved, except it was not. Because when researchers took the measured size and depth of that void and calculated how much cooling it would actually produce, the number came out far too small. Depending on the analysis, the void accounts for somewhere in the range of 10 to 50% of the temperature drop. Not the whole thing, S fraction of it. And a later study pushed harder, because a void that enormous would leave another fingerprint. Its gravity would subtly bend the light passing through it, and that bending is measurable in the same data. So researchers went looking for the lensing signature of a void large enough to explain the entire cold spot. It was not there. The lensing data disfavored the existence of a void that big. So not only is the void we found too small to do the job, the evidence argues against a bigger one hiding there. So after 20 years, the leading conventional explanation covers part of the problem and leaves the rest open. But now I have to give you the other side, because I promised you honesty, and this cuts against the story I have been telling. There is serious recent work suggesting the cold spot may be less significant than it first appeared. The argument is about foreground contamination. That ancient light has to travel through everything between its source and us, including relatively nearby galaxies and gas, and those can leave their own imprint on the temperature we measure. Some researchers have argued that once you carefully account for certain nearby structures, the anomaly shrinks considerably, in some analyses down below the threshold, where anyone would call it unusual at all. If that work holds up, the cold spot stops being a mystery. It becomes a measurement artifact with a mundane explanation, and it drops out of this story entirely. So where does that leave us? Honestly, unresolved, the cold spot is a real feature in the data. That much is not disputed. What is disputed is how meaningful it is. Some researchers regard it as a genuine anomaly that our best conventional explanation cannot fully account for. Others regard it as a statistical fluctuation dressed up by contamination. Both camps are made of serious people, and the argument is ongoing. I would rather tell you that than hand you a clean answer that does not exist. Because you will find plenty of places online where this gets presented as settled proof of something extraordinary. It is not. It is a 20-year-old open question that may yet turn out to be nothing. But keep it in mind, because of something we will come back to later. The cold spot has a rough shape and a rough temperature profile. And decades ago, before it was ever found, some theorists worked out what a very particular kind of event would leave behind in this exact light. We will get to whether those two things match. First though, there is a third crack, and this one may be the largest of all, because it concerns the thing that makes up most of the universe. That is where we go next. So here is the third crack, and it concerns the largest single component of the universe. Let me take you back to 1998. Two independent teams were measuring distant exploding stars, trying to answer a straightforward question. The universe is expanding, and gravity pulls everything together, so the expansion must be slowing down. The question was how much? they both got the same answer, and it was not the one anyone expected. The expansion is not slowing down. It is speeding up. Something is pushing the universe apart, and it is winning against gravity. That discovery earned a Nobel Prize, and it forced a new ingredient into the model. We call it dark energy, and by our best accounting, it makes up around 68% of everything in existence. The largest component of the universe, and we do not know what it is. Now, the standard assumption about dark energy is that it is constant, the same everywhere, the same strength for all time, an unchanging property of space itself. It even has a home in Einstein's equations, in a term he wrote down long before any of this. That assumption is baked into the model, and everything else is calculated on top of it. So, the obvious thing to do is check it. And to check it, you need to measure the expansion rate not just now, but across cosmic history, and see whether the push has been steady. That is what a project called DESI was built for. Every clear night, it collects light from thousands of galaxies at once, measuring how far away each one is. Over years, that builds into the largest three-dimensional map of the universe ever made. And because looking further away means looking further back in time, that map is really a history. In March of 2025, DESI released the results from its first 3 years, covering roughly 14 million galaxies and quasars. And the results suggested something the model does not allow. Dark energy may not be constant. When the data was fitted, the preferred picture was one where the push has been changing over time, apparently stronger in the past and weakening as the universe ages. If that is true, it is a serious problem. A constant does not change. That is what makes it a constant. If dark energy evolves, then this piece of the model is not describing the universe correctly, and a great deal built on top of it has to be revisited, including possibly the Hubble tension itself. So how strong is the evidence? Here I have to be precise, because this is exactly where reporting tends to go wrong. The significance depends on which supernova dataset you combine with the DESI measurements. Across the main options, the preference for evolving dark energy over a constant comes out somewhere between about 2.8 and 4.2 sigma. Now recall our earlier discussion. Physicists treat 5 sigma as the discovery threshold, so even the strongest of these numbers sits below that line. It is meaningful, it is not nothing, but it is not a discovery, and the DESI collaboration has been careful about saying so, and there is a real objection that deserves airtime. Several groups have argued this preference is not as robust as it looks. The result depends on combining 3 different kinds of data, and those datasets are themselves in mild tension with each other. So a model with more flexibility, like one where dark energy can evolve, may be winning simply because it smooths over disagreements between datasets, rather than because it describes reality better. One reanalysis using a recalibrated supernova sample found the evidence essentially disappeared. So, the honest position is this: there is a real and growing hint that dark energy is changing from the most capable survey ever run. It has strengthened since the earlier data release rather than fading, and it is not yet strong enough to call a result, with credible researchers arguing it may dissolve under closer inspection. More data is coming, and this will be settled one way or the other in the next few years. So that is our third crack. Add them together, and the picture is this: a number that refuses to agree with itself past the discovery threshold. A patch of ancient light, our best explanation, only partly covers, which may or may not be real, and a hint that the dominant component of the universe is not behaving as assumed. 3 problems in 3 different kinds of data, and now we come to the strange part of tonight's story. Because there is a theory that anticipated something like this, and its own mathematics has been insisting on something remarkable for over 40 years, that is where we go next. So now we leave the anomalies for a moment and look at the theory. Because there is something built into our best account of the first instant of the universe that most people find genuinely startling when they first meet it. The theory is called inflation, proposed in 1980 by a physicist named Alan Guth, and the claim is extreme. It says that in the first fraction of a second, far less than the blink of an eye, the universe underwent a burst of expansion so violent that a region smaller than an atom was stretched to something enormous. Then it stopped, and the ordinary, gentler expansion we still see today took over. That should sound like an outrageous thing to propose, and it would be if it were invented to be dramatic. It was not. Inflation is taken seriously because it solved 3 specific problems that had no other good answer. The first is the horizon problem. Look at the oldest light coming from opposite sides of the sky. Those 2 regions are so far apart that in the entire history of the universe, no light or heat could ever have traveled between them. They have never been in contact, and yet they are at almost exactly the same temperature. That should be impossible. Things do not match temperature by coincidence. Inflation explains it. Before that burst, the whole region was tiny and in close contact, so it evened out. Then inflation stretched that already matched patch into everything we can see. The second is the flatness problem. Space appears to be geometrically flat to remarkable precision, but flatness is a knife edge. Any tiny deviation early on would have amplified enormously over billions of years, leaving a universe obviously curved. For it to still look flat today, the early universe would have to have been fine-tuned absurdly. Inflation solves it naturally. Stretch any curved surface enormously, and the part you can see becomes flat, the way the ground under your feet looks flat on a round planet. The third is the origin of everything. Where did the structure come from? If the early universe had been perfectly uniform, gravity would have had nothing to work with, and there would be no galaxies, no stars, no us. Inflation says the seeds were quantum fluctuations, the tiny random jitters that exist even in empty space, stretched to cosmic scale by that violent expansion. And this one was testable. If the structure of the universe grew from stretched quantum jitters, then those fluctuations should have left a specific statistical pattern in the oldest light. That prediction was calculated, then it was measured. It matched. That is the very pattern we discussed earlier. So inflation earns its place. 3 deep problems, 1 solution, and a confirmed prediction. But it comes with a passenger that many physicists would rather not carry. Inflation is driven by a field, a kind of energy-filling space that fuels the expansion. And for inflation to end, that field has to decay into ordinary matter and radiation. Here is the catch. Quantum mechanics does not let things decay on a schedule. It decays probabilistically. Some regions convert early, some late, and some simply have not yet. So picture what that means. In some patches, the field decays, inflation stops, and a universe settles down into something like ours. But the space between those patches is still inflating, and inflating space grows at a staggering rate. It creates new volume faster than the decay can consume it, which means the process never fully ends. Somewhere, inflation is always still going, always producing more space, and within that space, new regions keep dropping out and becoming universes of their own, bubbles forming in an endless expanse. This is called eternal inflation, developed in the early 1980s, particularly by André Linde. And this is the point worth sitting with. Nobody set out to invent a multiverse. Inflation was built to fix 3 specific problems, and it did. The endless production of other universes came out of the mathematics uninvited as a consequence of taking the theory seriously alongside quantum mechanics. Now let me flag the honest limits. Inflation is well supported but not proven, and there are competing models. And not every physicist accepts that eternal inflation follows inevitably. Some argue the reasoning breaks down in ways we do not yet understand. This is a live debate, but the mainstream position is uncomfortable and clear. Our best theory of the beginning implies our universe is one of many, which raises an obvious question. If bubbles are constantly forming in an inflating expanse, they are not necessarily isolated forever. What if two of them touched? And would we be able to tell? That is where we go next. So if our universe is one bubble among many, and bubbles form constantly in an expanding background, then sooner or later two of them will touch. And this is where the idea stops being philosophy and becomes physics. Because a collision would do something, it would leave a mark, and theorists worked out, decades ago, exactly what that mark should look like. Here is the reasoning. Our bubble has a wall, the boundary where inflation ended and our universe began. If another bubble expanded into ours, those two walls would meet, and the collision would send a disturbance rippling inward through our bubble. That disturbance would slightly alter the density and temperature of everything it passed through, including the plasma that later released the oldest light we can see. So the signature would be printed into the cosmic microwave background, and its shape is not arbitrary. Because a collision comes from one direction, the mark would be a disk on the sky, round, centered on the direction the other bubble came from, with a distinctive profile, a specific way the temperature changes from the center outward, and a relatively sharp edge where the disturbance stops. Around 2011, a team built an algorithm to scan the microwave sky systematically for exactly this signature, not by eye, which invites the temptation to see patterns, but computationally, searching for circular features with the predicted profile. It ran across the whole map. It found 4 candidate regions worth a closer look, and that generated real excitement, because a candidate is not nothing. Then better data arrived. The next satellite mapped the microwave sky with substantially higher resolution and sensitivity, and the search was run again on that much sharper map. And the answer came back negative. No statistically significant detection of a bubble collision signature anywhere in the sky. The earlier candidates did not survive the better data. What had looked promising in a coarser map dissolved when examined more closely. That is the honest result, and I am not going to dress it up. The most direct search for evidence of a collision with another universe has been conducted carefully with the best data available, and it found nothing. Now, what about the cold spot? It is roughly circular, which is suggestive, and this connection does get raised. But when researchers compared the cold spot properly against the predicted collision signature, the match was not good enough. The predicted profile has particular features, and the cold spot does not reproduce them convincingly. Its temperature falls off in the wrong way. It lacks the sharp edge the models call for. Some analyses found it not entirely inconsistent, which sounds encouraging until you realize how weak a statement that is. Not inconsistent is very far from consistent. So the honest position is that the cold spot is not evidence of a bubble collision. It shares one broad characteristic with the prediction, its rough roundness, and fails to match the details. Now, a null result is not the end of the story, and here is why it still matters. When you search for something and find nothing, you learn something real. You place limits. This search tells us that if our bubble collided with another, the collision was not close enough, or violent enough, or recent enough to leave a mark our current instruments can detect. That rules out a whole range of possibilities. It narrows the field. And there is a further complication that is worth being clear about. Collisions may simply be rare, or their marks may be far too faint. In much of the parameter space these models allow, you would expect no visible signature at all, even if collisions happen constantly. So finding nothing does not disprove the multiverse. It just means we have not caught one this way. So we have run the most direct test available, and it came back empty. But a collision is not the only kind of boundary that theory allows. There is another sort, one that would not be a past event leaving an echo, but a structure that still exists right now. And the strange thing about it is that it comes straight out of Einstein's own equations in a form he did not want. That is where we go next. So there is another kind of boundary that theory allows, and it is stranger than a collision, because it would not be a past event that left an echo. It would be a structure that exists right now. They are called domain walls, and to understand what they are, start with something ordinary. Think about water freezing. It does not freeze uniformly everywhere at once. Ice crystals begin forming in different places independently, each growing outward with its own orientation. When two of those regions meet, they do not blend smoothly. There is a seam between them, where two differently oriented crystals press against each other. Now take that idea and apply it to space itself. In modern physics, space is filled with fields, and some of those fields can settle into more than one stable state. Different states with the same energy, equally valid, and the field simply has to pick one. And in the early universe, as things cooled, different regions of space would have made that choice independently, just as different patches of water freeze independently. So what happens where two regions that chose differently meet? You get a boundary, a surface where the field transitions from one state to the other, and that surface is a domain wall. Here is what makes it so unlike anything in your experience. A domain wall is not made of matter. It is not material sitting in space. It is a feature of space, a seam in the fabric where the underlying field changes its mind. It carries energy spread across its surface, and its gravitational behavior is genuinely peculiar, unlike that of any ordinary object. And I want to be clear that this is not fringe speculation. Domain walls are a standard, well-studied consequence of field theory. They appear across decades of published work. If the early universe went through certain kinds of transitions, walls of some sort are expected. This is textbook physics. But here is the important part, and it cuts against the exciting version of this story. Domain walls are severely constrained by observation, and the reason is that they are heavy in a very particular way. A large wall carries an enormous amount of energy across its surface, and as the universe expands, that energy does not dilute the way ordinary matter does. So, if sizable domain walls existed in any abundance, they would quickly come to dominate the energy of the universe entirely. We would see the consequences. The oldest light would be far more distorted than it is. The expansion history would look completely different. The universe would not look anything like the one we observe. So observation tells us that if domain walls exist at all, they must be extremely rare or extremely light or pushed far outside anything we can see. This is not a case of physicists ignoring an exciting possibility. It is a possibility that has been examined and heavily restricted by evidence. Now, there is a further idea, and I am going to flag this clearly before I say it, because we are now moving well past what is established. Some theorists have explored whether the energy associated with a boundary of this kind could contribute to what we observe as dark energy. The reasoning goes that a wall carries energy. That energy affects the geometry around it, and from inside, an effect of that sort might look like a smooth push spread through space with no local source, which is, broadly, how dark energy appears to us. I want to be precise about the status of that idea. It is a theoretical exploration. It is not a measurement. It is not a leading explanation, and there is no observation pointing to it. It is the kind of thing that gets worked through in papers to see whether the mathematics permits it, which is a legitimate activity, but a very long way from evidence. If you encounter this presented as a discovery, it is not one. So let me summarize honestly where domain walls leave us. They are real solutions in well-established physics. Einstein's equations permit boundaries of this general kind, whether or not anyone finds that comfortable. And we have no evidence that one exists anywhere near us, with observations placing tight limits on how common they could be. That is the full picture, and I would rather give you that than a cleaner story. So, we have reached the end of the evidence. 3 anomalies, a theory that keeps insisting on other universes, a direct search that found nothing, and a class of boundary that is permitted but constrained. Now we have to do the hardest part, which is add it all up honestly and say what it actually amounts to. That is where we finish. So let us add it up honestly. We have a number that disagrees with itself, past the threshold physics uses for a discovery, with the most comfortable explanation now firmly ruled out. That one is real, and it is not going away. We have a cold patch in the ancient light, our best explanation only partly covers, which some researchers argue may not be an anomaly at all once the foreground is handled carefully. Unresolved and genuinely contested, we have a hint that dark energy is changing rather than constant. From the largest survey of its kind, sitting below the discovery threshold, with credible objections that it may be an artifact of combining datasets that disagree. Suggestive, not settled. We have a theory of the first instant, well supported and confirmed in its predictions, whose own mathematics implies that other universes exist, not as a flourish, but as something difficult to avoid once you take it seriously. And we have the direct test, the search for a mark left by a collision with another bubble, run properly across the whole sky with the best data we have. It found nothing. So what does that amount to? It amounts to this: there is no evidence that anything outside our universe has been detected. None. Not a signal, not a boundary, not a wall. Anyone who tells you otherwise is selling something. What we have instead is a model that is under strain in several places at once, and a theoretical framework that, if correct, means our universe is one of many. Those two facts sit next to each other, and nobody can currently say whether they are related. That is not a dramatic ending, but it is the true one, and I would rather leave you with an accurate picture than an exciting fiction. Here is what makes this a genuinely interesting moment rather than a shrug. All of this is about to be tested properly. A new observatory has begun surveying the entire southern sky night after night, building a record of the changing universe more complete than anything before it. A space telescope is mapping the geometry of the cosmos across billions of light years, specifically to measure whether dark energy has been constant. DESI is still collecting, and its next releases will either strengthen that hint or dissolve it. And a new generation of instruments is being built to measure the oldest light with a precision that would make our current maps look coarse. So, within the next decade, most of tonight's open questions will move. The Hubble tension will either be explained or force a change to the model. The dark energy hint will either cross the threshold or fade. And the cold spot will either survive better analysis or quietly stop being a mystery. We will not have to wonder indefinitely. That is not nothing. Think about what it takes to be in the position we are in tonight. To notice that 2 measurements of the universe disagree by 9%, you have to measure the universe twice, in completely different ways, each to within a few percent. To worry about a patch of sky being 70 millionths of a degree too cold, you have to measure the temperature of light released 13 billion years ago across the entire sky to that precision. To argue about whether dark energy has shifted slightly, you have to have mapped 14 million galaxies. Every problem we discussed tonight only exists because our instruments got good enough to find it. These are not the mysteries of people staring at the sky and wondering. These are the mysteries of a species that has measured carefully enough to see where its own understanding stops. And that is what I find quietly extraordinary. We built machines precise enough to locate the edges of our own ignorance, not to eliminate it, but to map it, to be able to say, with real numbers attached, here is exactly where our picture of reality stops working. There may be other universes, there may not be. Tonight, honestly, we do not know, and We may not know for a very long time, but we are the first creatures on this planet who can ask that question and then design the experiment. Who can take something that sounds like pure fantasy and turn it into a search across the sky with a specific prediction and a real answer? That is not proof of anything beyond our universe, but it is proof of something about us. Thank you for sitting with the honest version of this story tonight. If you found it worthwhile, share it with someone who prefers real questions to easy answers. And if you would like to keep exploring the edges of what we actually know, twice a week, you know what to do. Until the next journey, rest well, keep wondering, and never stop looking up.